Hi everyone, this is Jim. Welcome to my channel. One thing you might have noticed while reading books for deep learning is that some people term neural network as black boxes. We know that neural networks do have a well-defined mathematical structure, but they are still being referred to as black boxes due to the fact that it works end-to-end all the time. And most of the case, we can't really understand the decisions made by a deep neural network. For instance, let's consider a dog versus cat classifier, which is a quite simple convolutional neural network. The decision made by the network is the class predicted for a given image, whether the image contains a dog or a cat. During the inference process, the intermediate process is pretty much unknown. Decoding a decision would help us investigate the features of the input image and also figure out some important features which might be major contribution in producing that particular prediction. Could be its floppy ear, innocent eyes, lovely tongue, wavy hair, fascinating fur, or any other features which distinguish it from the other class. We like to know on what basis our model predicts a certain label, like a cat or a dog. In order to identify such features and also to discover the focus of the neural network for a particular decision, we need to introduce that concept of explainable AI. In this video, we are going to cover some aspects of a pioneer explainable AI technique, which are named as CAM. Starting from the paper, followed by mathematical equations and coding analysis to figure out the idea behind the things. Alright, let's dive in. CAM stands for Class Activation Map. It's one of explainable AI techniques, which uses feature visualization to explore the mechanism of convolutional neural networks. Essentially, it maps the output of the classification back to the original image, hence intuitively telling us which part of the image has a great influence on the final classification result. For example, if we had a cat and a dog in an image, CAM tells us which part of the image led it being predicted to be a dog and which part of the image led it being predicted as a cat. It helps us to understand the principles and decision-making process of neural networks, so we can better design the network. Referencing CAM puts forward some higher requirements for the model. Not only the accuracy, but also requires the network to extract the features that we need. We can also leverage CAM to guide the model to learn better. For example, we can use CAM to augment the dataset by erasing or cropping. In addition, since CAM pay close attention to the target, it can deal with some semantic segmentation or object detection tasks, which greatly reduce the labeling workload, but this usually requires a highly accurate CAM. In practice, we extract the CAM from the last convolutional layer of the network, because other subsequent operations, such as fully connected layer, will cause the loss of spatial information, making the feature information output by it impossible to be intuitively understood by human. Usually, the feature map of each convolutional layer will have many channels. For example, the last layer feature map of ResNet 18 has 518 channels. These channels can be considered as features that be extracted from different dimensions, which are highly abstract. And each channel contributes differently to the final result. So, visualizing each channel separately to obtain every heat map is also difficult to understand. Therefore, the general CAM equation is based on the different contributions of each channel. Generally, the actions of CAM equation are nothing more than 4 steps. Step 1. Locate and extract target feature maps that need to be visualized. Step 2. Determine the weight of each channel of the feature map in some way. Step 3. Project the feature map along the channel axis by weighted average to a 2D map. Step 4. Normalize the heat map. Resize it by interpolation, then overlay upon the original image. As of now, there are more than 10 variants of CAM implementations. Here are 7 CAM-related papers listed in chronological order, some gradient-based and some gradient-free. But either way, the main difference lies in the way that weights are determined in the second step. Let's get to this paper, the pioneering work of the CAM series. It's the one of the earliest method in this regard that published in 2015 by Joe Bolle et al. Basically, they proposed the CAM technique, which allows convolutional neural network to both classify the image and localize class-specific image regions in a single forward pass, e.g., the toothbrush for brushing teeth and the chainsaw for cutting trees. Let's look at this figure. The idea is that taking a convolutional neural network that uses a global average pooling layer to achieve the objective. Say, if we have 5 to 6 convolutional layers in the backbone of the model, and we take the last convolutional layer as the target feature map to perform the CAM acquisition. Now, please follow me to find out the idea behind the mathematical statements in this paper. Capital Fk equals summation of x and y, Fk of x and y. Capital F superscript here represents the result of performing the global average pooling at k's feature map layer, which is a scalar. And because global average pooling is simply taking the average of the k's map. And Sc equals summation of k, wk superscript c, capital F k. Here Sc represents the prediction score of a given class C, and wk superscript c is the weight corresponding to a class C for unit k. Let's take the capital Fk extension into the class score equation here. So we get a new class score equation down here, which equals to summation of k, wk superscript c multiplied by summation of x and y, fk of x and y. After that, according to distributive attribute, we can put the summation symbol of x and y in the front. Now we define IMC as the class activation map for class C, where each spatial element is given by MC of x and y equals summation of k, wk superscript c, fk of x and y. So here MC is just how we define the class activation map. Don't overthink it. So that we can denote class score by MC, which is the class activation map. In other words, we established a certain connection between the class activation map and the classification result SC. Hence, MC of x and y directly indicates the importance of the activation as partial grade x and y, leading to the classification of an image to class C. Therefore, if we upsample MC and overlay it upon the original image, we can observe which area that the model pays attention to in classifying a certain label. Maybe the mathematical equation doesn't give you a good sense of what we are doing. Let's look at the figure again, and you will find that this is essentially the first steps in the CAM equation we just mentioned earlier. First, we identify the target feature maps located in the last conv layer of the model. For example, in ResNet 18, it has 512 channels in the last convolutional layer. Next, each layer is extracted from the feature map set. We take this green feature map and average all the intensity value into one single scalar that becomes the green circle here. Then, by taking the right feature map and average all its value, it becomes the right scalar here. We take layer by layer all the way to the last blue feature map. Similarly, average all the values and it becomes the blue scalar here. After having these global averages that each of these scalars represent one feature map, we learn a simple regression model of a linear layer that takes this scalar to each of the class labels on the last layer. So for each of the class labels, we learn W1 from the first feature map average, W2 from the second feature map's average, and so on and so forth until Wn, where n is the number of feature maps in the last convolutional layer. In step 3, the weights that we learned between the gap layer and the classification layer are now used to weight each of these activation map layers. And then we do a weighted summation of all these activation maps that gives us the contribution of these activation maps towards one particular class label. And in this case, the weighted combination of activation maps of that conv layer corresponds to the prediction of Australian Terrier. Now, this CAM approach gives us a way of getting class discriminative mapping, explains us which part of the image has a positive influence on the final classification result. Now, I will give a live demo of a PyTorch CAM coding implementation. Some popular neural networks, such as ResNet and DenseNet, already have global average pooling at the end, so we could generate the heat map directly without even modifying the network architecture. For the convenience of the demonstration, I choose ResNet 34 and directly load the model from Torch Vision, as well as the pre-trained weights that trained on the ImageNet 1000 classification dataset. After model loading, we need to download the ImageNet class labels from internet and store them into a list named as classes. Then, let's check the ResNet 34 architecture by printing the model. ResNet has three main parts: stem, stages, and head. Stem is the first convolution layer with an optional pooling layer followed by a ReLU activation function. Layer 1 to layer 4 are 4 stages which are grouped residual blocks, and each stage include multiple residual blocks. The head include a average pooling layer followed by a fully connected layer. This head architecture has inherent compatibility with CAM. The weights required in CAM are exactly the weights here in the last linear layer, so we can leverage these parameters directly. Next up, we define the transforms chained together composed by two tensor and normalize to perform some manipulation on the image and make it suitable for model inference. After that, we load in the test image with two dogs running. The one on the left is a Corgi, the other one on the right is Yorkshire Terrier. Now let's perform a forward propagation and take a look at the top 5 inference result. I believe the model is doing pretty well. Although there is no Corgi in the top 5 prediction result, the Yorkshire Terrier on the right is accurately predicted, and the confidence score is far higher than any other classes. Next, we need to modify the model structure to obtain the CAM, starting by defining a new model which removes the last two layers from original model sequential. Then we load the image and transform it into a suitable format. After that, we extract a subset of weights only for a certain class index from the last fully connection layer. Then we perform the new model's forward pass, get the feature map, weighted average these feature map layers by multiply the extracted weights. Once everything is in place, we can perform the visualization. Let's first perform CAM extraction on the classification of Yorkshire Terrier, which category index in ImageNet is 187. According to the CAM overlay image on the right, we first confirmed that the prediction is reasonable. The heat map area are pretty much focused on Yorkshire Terrier. After careful observation, we found that the area with the largest activation is concentrated on the face, wavy hair, as well as the legs. Next, we perform CAM extraction on the classification of Corgi, which category index in ImageNet is 263. Similarly, according to the CAM overlay, we found that the area with the largest activations are concentrated on the Corgi's ear, face, and its undeniably cute short legs. For those models that are not compatible with CAM, such as VGG, which does not use global average pooling and has multiple fully connection layers at the end, we have to make modifications to the architecture, replace all the fully connection layers with one single global average pooling layer, as well as one single fully connection layer, which forces us to retrain the network and led to burden on computing resources. In practice, we only retrain the base of the last fully connection layer and freeze all the rest parameters in the backbone of the network. To conclude, as the first work of the CAM series, it provides a perspective to help people intuitively understand the black box model and also help with the model improvement. However, it requires modification of the model structure and model retraining, which greatly limits the use cases. If the model is already released, it is almost impossible for us to retrain for this CAM. I'm gonna talking about Great CAM in my next video, which just solved this problem. We've still got lots more to come, so please stay tuned and have a good one. I will see you soon.